had an algebraic interpretation and a geometric one. So first of all, geometrically, if we take two vectors, we can call them u and v, right? We're often interested in finding the angle between them. And the scalar product, or the dot product, we often called it, is the key to working that out, right? Because there was a property that told us that the dot product of two vectors was also equal to the magnitudes multiplied together multiplied by cos theta, right? An interesting property happens, I'll close it in a sec, when we have right angles. What happens when we have right angles? They are right angles? Yeah, cos 90 is 0. Okay, so when we have a situation like this, if you substitute in theta as 90, right, cos 90 would just be 0, which means that the dot product would be 0 as well. So that still holds true here, right? So when theta equals 90 degrees, dot product is 0. And what that does is opens up problems so that we can think about something like this. So we got some ideas. How for the first one? Not too bad? All right. James, walk through it with me. All right. Yep. So again, right, like two definitions of dot product that we need to know. We need to know this kind of component where we're multiplying, when we're taking these multiplied together with their respective like I, J, K components and then summing them up, right? So we've got A dot B. That's just going to be lambda times lambda minus 1 plus 1 times 2 and yeah, and 2 times 4, negative 4. And then what are we going to do with that?
So then you like explain everything else.
Cool, yep.
Plus 2 minus 8.
Yep.
And then put the 6 to the other side from the plus 2 minus 8.
Yeah, so this guy's negative 6.
So that will equal 0.
Right, so that's the key part, right? We're in the perpendicular, we want to let A dot B equal 0, so just tell people what you're doing, right? And it's okay, because for perpendicular values, and then you can solve that like a, what do you want to do with the 6, sorry?
Just solve like the,
Yeah, right, solve like quadratic, should be getting lambda minus 3, lambda plus 2. And how do you like that? Right, and if they were asking for the vectors, you'd probably, and I think the original question did, you'd actually have to write out the actual vectors that you create as well, okay? So just make sure you're answering the question there. This one is kind of interesting because like I said, right, it's hard to represent things, a 3D kind of vectors on a diagram, especially when you're constructing them yourself. Even with GeoGebra and stuff like that, it's sort of hard to visualize exactly what's going on, right? We knew though from last lesson that we can develop these distance formulas and things like that. What was that distance formula, Matt? How do I get this one?
There's one to us like 2 times 3 squared.
Yeah.
And then 2 squared.
Does the order matter?
No.
No, because you're squaring them. So I think, like the order doesn't matter obviously for the result here, but I think it's the habit of like AB is represented by B minus A is what I mean. Does that make sense? Minus 3 all squared and 4 minus negative 1. And what is that? 1 squared plus 5 squared plus 5 squared. See, okay. Angle between A and B, Angus?
Sorry?
Angle between A and B? Oh no, should be. Dot product?
I'm going to get by B. times 3.
Yep.
Potentially I plus 3 times minus 2j. Plus minus 1 times 3.
See?
The first 2 cancel out.
Yeah, it's nice, isn't it? -4. Angles now. So now we can do the angle, right? Because we have a few different definitions for this. We can say that this is the dot product, but what's the other definition? Well, the other definition is that we have A, B, their magnitudes multiplied together, cos theta is also equal to the dot product, which we have a few pieces now. We have this piece. The angle between the two vectors, that's right, yeah. So go ahead and find our magnitudes, and then work these guys out. Alright, so for our magnitudes, we should get something like this. So I'm going to calculate for that one. I'll probably do it in my head. 4, 9. Wait, that one's looks familiar. Is that root 14 again? Yeah, we need to get creative with these numbers. And this guy is root 29. Seem right? Okay, cool. So I put them all together, so I get root 14 times root 29 cos theta equals to -4. Don't need to put these two together. We can just solve by rearranging and then taking the inverse. And theta should equal to, yeah, someone can do that.
Do you want to do radians?
Let's go degrees, nearest degree maybe.
I got 101.
Yeah, 101 degrees, and let's do that.
Is that?
I should write out the full working. What's the minutes and stuff? 7 minutes. 101 degrees, nearest degree. All right, last one is interesting. Yeah. All right, so we can verify all this stuff, by the way, right? Like, so we're thinking about the angle between vectors A and B. All right, so over here, right? Here's our vector A. Here's our vector B. And this angle, yeah, kind of looks acute from this perspective, but I don't know, I'd believe that. Maybe it's just the perspective of the angle. Don't know if I can. I think this is the problem with 3D, right? Because, yeah, you need to like look at it from the right perspective. Because if it's creating a parallelogram, right, so this is the last question. The coordinates of C of A or BC is a parallelogram. Like, which plane or which perspective do we look at the angle from? I think I had it like this before, which I thought was right, but I think that's not quite right, because you can see that the B sort of offshoots onto the distance a bit. So I think the right perspective would be like, I don't know. I feel like I had it before. Like, I'm trying to make this look like a parallelogram. Yeah, so there you go. That looks a bit better. The angle between them, yeah, I believe that's 101, right? C though, where does C go? That's the question. To make this work, to make this look like a parallelogram, roughly where should C go, do you reckon? Here? Further up or further down? Here, do you reckon? Would you believe that's a...
Yeah, bit down, bit in.
Bit down, bit in. So like here. That looks like a trapezium. Anyway, somewhere around there. Somewhere around there, right? I guess the question is, how do we find it? What do we add?
There's some sort of like parallelogram rules.
Parallelogram rule. Is there a parallelogram rule?
I don't know, we're doing something about parallelograms in section 1.
I mean, we roughly have an idea of where it is. Okay. And we do want to be thinking about our extension 1 rules, actually. And there is actually a parallelogram rule.
B plus A?
What is B plus A? Well, that's exactly right. B,
Vector A
Yeah, B plus A, if you think about it, right, in extension 1 we learned the parallelogram rule. Another application of that, again, it can be applied to 3D, is that the vector C here is actually defined geometrically by taking vector A plus vector B, and we actually create that diagonal of the parallelogram. And the diagonal of this parallelogram is actually the vector that we're looking for, okay? So by finding the sum of these two, we can actually find that, right? So using the parallelogram rule, that's right over here, using parallelogram rule, or law, I think it's called the law. Right? A plus B would equal to C. And so we just sum them together. Again, when you're summing them, same idea, right? You just sum up the IJK components. So we'll get 2 plus 3 plus 3 minus 2 and minus 1 plus 4. So we get 5i plus j plus 3k. And let's see if this actually looks right, or how close we were. So, C is equal to 5, 1, positive 3. Yeah. Oh, we're actually pretty close. That's not bad. Oh, that's not bad. That's not bad. That's pretty good, actually. Dude, we were pretty good. I mean, my dot was massive, but, you know, it's not bad. So I've had a good chance of getting it. Okay, cool. So that's this idea of 3D vectors, right? We use our extension 1 knowledge, same formulas, same concepts and things like that, and we can apply them in a 3D context. Again, the hard part is like visualizing what's going on. But for the most part, I think we will be focusing on a calculation perspective, like I said, right? They'll give you these coordinates and they'll ask you these kind of questions.